Good morning, friends. My topic of discussion today will be the concept on partial differential equations, which is module 3 in engineering mathematics 2 with subject code 15 MA 21. I am Dr. R. Murli, Professor, Department of Mathematics, Dr. Ambedkar Institute of Technology, Bangalore. In partial differential equations, we will look into the following topics. First, what is a partial differential equation? In short, written as PDE. How to form a partial differential equation? Solution of non-homogeneous PDEs by a direct integration procedure. Solution of homogeneous PDEs involving derivatives with respect to one independent variable only, and the heat and wave equations followed by the solutions of these equations using variable separable method. So, in today's lecture, we will be defining a PDE, what is a partial differential equation, then how to form a PDE. Now, a partial differential equation has in it the words differential equation. So, obviously, a partial differential equation is something related to a differential equation, and you know, friends, that a differential equation is something containing the derivatives. So, we begin with the definition of a partial differential equation. An equation involving one or more partial derivatives of a function of two or more variables is called a partial differential equation, in short also written as PDE. Now, throughout partial differential equations, we will consider Z to be the dependent variable. Z is the dependent variable which depends on the independent variables x and y, and the partial derivatives of Z with respect to x and y are known, and they are the first order derivatives dou z by dou x and dou z by dou y. So, these are the first order partial derivatives. Then we have the second order partial derivatives dou square z by dou x square, which is the derivative of z twice partially with respect to x. You have dou square z by dou x dou y, which is the partial derivative of z with respect to both the variables x and y, first y and then x, and you know that it is immaterial how you differentiate, in the sense dou square z by dou x dou y is dou square z by dou y dou x, and finally the partial derivative dou square z by dou y square, which is the differentiation of z two times with respect to the variable y. Our syllabus is restricted up to the second order derivative. So, we will be looking into examples where we form PDEs maximum up to the derivatives containing second order. So, next, the order of a PDE is defined as the order of the highest derivative present in it. So, go to the PDE, find out the partial derivative present in it which is of the highest order. So, the order of that derivative becomes the order of the PDE itself. Next, the degree of a PDE is the degree of the highest order derivative. Go to the previous definition, go to this, identify the highest order derivative, take the power of that is the degree of the highest order derivative present in it after clearing the equation of all fractional powers. If you have fractional powers, remove the fractional powers, right? The corresponding integral power of the highest order derivative present in the equation becomes the degree of the PDE. Next, if the dependent variable you can see, friends, is z, Okay. In our discussion, we will take z as a dependent variable. So, if the dependent variable and its partial derivatives in a PDE are of first degree, then the PDE is said to be linear, linear PDEs. Then a PDE is called homogeneous if each term in it contains either the dependent variable, that is z, or one of its partial derivatives. So, exclusively it should contain either the dependent variable or one of its partial derivatives. Such equations are said to be homogeneous partial differential equations. Otherwise, the PDE is said to be non-homogeneous. Before we go to the formation of PDEs, let us look into some examples. The first example, 2 dou z by dou x plus 3 into dou z by dou y is a homogeneous PDE of order 1 and degree 1. You can observe it is order 1 because there are two partial derivatives dou z by dou x and dou z by dou y, both are first order, and the degree of, that is the power of the partial derivative is 1. So, it is a PDE of order 1 and degree 1. Further, it is homogeneous because it contains the dependent variable and its partial derivatives, that is you have dou z by dou x and dou z by dou y both. Similarly, the second equation, dou square z by dou x square plus dou square z by dou y square equal to 0 is a homogeneous PDE. Why order 2 friends? Because the highest order derivative is dou square z by dou x square, or both the derivatives present in the equation are of order 2, and the degree is 1 because the power of these partial derivatives, okay, the highest order derivative is equal to 1. Next example, if you observe the next example, the highest order derivative present is dou square z by dou x square. So, the PDE is of order 2. The power of dou square z by dou x square is 1. So, it is of degree 1. Further, it is non-homogeneous because, observe the RHS friends, it is x plus y. So, the definition says it should contain either the dependent variable or its partial derivatives. So, because of that, this equation becomes non-homogeneous. Next, similarly, dou square z by dou x dou y minus 4xy equal to 0 is non-homogeneous. It is of degree 2 because, sorry, order 2 because this is dou square z by dou x square is a second order partial derivative and its power is 1. Hence, the equation is said to have degree 1. Likewise, the last two examples, x dou z by dou x plus y dou z by dou y equal to z is linear, which is of order 1 and degree 1, and it is also non-homogeneous. And finally, in the last example, observe that the highest order derivative is dou square z by dou x square. So, the order is 2, but the integral power of dou square z by dou x square is 2. So, you say it is degree 2 and the equation is also non-homogeneous. After these examples, we will go to the formation of a PDE. Now, when you form a PDE, there are two methods to do this. First, PDEs can be formed by the elimination of arbitrary constants from a relation. So, a relation will be given, that relation will be containing a few arbitrary constants, okay. And I think the best way to remove constants, I think you know friends, is by differentiation. So, just differentiate to remove the constants. So, first PDEs can be formed by two methods, either by the elimination of arbitrary constants from a relation or by the elimination of arbitrary functions from a relation, and both these elimination procedures can be done by partially differentiating the given expression or the given relation. Now, there are some specific conditions for formation. In the case of arbitrary constants, if the number of arbitrary constants is equal to the number of independent variables, like you see here, these partial derivatives that are written on the board have dependent variable as z with two independent variables x and y. Okay. So, if the number of arbitrary constants in the relation is equal to the number of independent variables, for example, you have 2 here, correct? We obtain a PDE of order 1, first order PDE, that is the PDE will contain the partial derivatives dou z by dou x and dou z by dou y. Whereas, if the number of constants is more than the number of independent variables, then we obtain a PDE of order 2 or higher. For example, you have 3 arbitrary constants, then if it exceeds the number of independent variables, then you get a PDE of order more than 1. But in the case of arbitrary functions, the order of the PDE is always equal to the number of arbitrary functions eliminated. But when eliminating arbitrary functions, constants if present need not be removed. That is to say, when you do a partial differentiation procedure, in the differentiation procedure, if the constants vanish, it is okay. Otherwise, if they do not vanish, they can remain in the equation as it is. The main aim when you eliminate arbitrary functions is to remove functions and not the constants. We will go to the first method as to how to form a PDE by elimination of arbitrary constants. So, as we mentioned earlier, we have the standard notations. We consider z as a function of 2 independent variables x and y. As I mentioned earlier, the first order partial derivative dou z by dou x is also given the notation zx. It is also called small p. So, this is p. Then the first order partial derivative of z with respect to y is given the subscript zy, also denoted by q. The second order partial derivative dou square z by dou x square is written as zxx, which is denoted by r. Then the second order partial derivative dou square z by dou x dou y is equal to zxy, which is also the same as dou square z by dou x dou y, dou y dou x. This should be dou y dou x. Okay, dou square z by dou y dou x, which is denoted by z yx, that is denoted by s. And finally, dou square z by dou y square, which is z yy is equal to t. Now, as far as these two partial derivatives are concerned, the first partial derivative is obtained by first differentiating z with respect to y and then with respect to x. We can use this reverse arrow procedure. First y treating x constant and then with respect to x, or you first partially differentiate with respect to x and then with respect to y. But both of these are equal and they are given the notation s. This is r and this is equal to t. Now, when you form a PDE by the elimination of arbitrary constants, you must make note of the following. The elimination of arbitrary constants is done by differentiating the given expression partially. So, if the expression contains 2 arbitrary constants, then p and q are sufficient. P and q in the sense p is dou z by dou x. So, differentiate the given expression once partially with respect to x and differentiate the expression once with respect to y to give you p and q respectively. So, if the equation contains 2 arbitrary constants, you should get a PDE of order 1, and almost all PDEs of order 1 will contain both p and q. If it has p, it also has q. Okay. Whereas, for more than 2 constants, we require higher order partial derivatives. We will precisely find out what is the order later in our examples. Why I am stressing this on this is that you should not differentiate the given expression any number of times. Okay. it is specifically dependent on the number of arbitrary constants in the relation. So, if there are two constants, you restrict the differentiation procedure to only dou z by dou x and dou z by dou y, do not go further. Okay. Let us look into a few examples on this. Form the PDE by eliminating the arbitrary constants from the following relations. Now, as far as the elimination procedure is concerned, the elimination procedure can involve one of the following. You can subtract, you can divide, you can multiply, etc. But the final expression or the PDE obtained should not contain the given arbitrary constants, whatever it may be. Okay. So, the elimination procedure can be by any known method like subtraction, division, multiplication and so on. The following examples will illustrate this procedure. We will go to the first example. Z is equal to x plus a into y plus b. Observe that these are the arbitrary constants. So, you are given z as a function of x and y containing two arbitrary constants a and b. So, as we told earlier, because I have only two arbitrary constants, I should restrict my derivatives to only p and q. So, we will start the differentiation. On differentiating partially with respect to x and y, we obtain, first take this z and differentiate partially with respect to x. So, what do you get? Dou z by dou x will be, which is p, differentiation of x plus a into y plus b, x plus a is 1, 1 into y plus b gives you p as y plus b. Again, differentiating partially with respect to y, dou z by dou y is, x is constant. So, differentiation of y plus b is 1. So, 1 into x plus a gives you x plus a. So, after you finish the differentiation, you should go for elimination. The elimination can be done by using p q and the given relation or only the derivatives, right, whatever method is suitable to the given expression. So, what we do here, multiply the partial derivatives obtained p and q. If you multiply p and q, I get p q equal to y plus b into x plus a, but y plus b into x plus a is nothing but the given expression z. So, that finally p q equal to z or z equal to p q is the required PDE, which you can see friends is a PDE of order 1. Let us go to the next example. Z square equal to x square by a square plus y square by b square. Notice in this expression that again there are two arbitrary constants, they are just a and b. The important thing is that it is the arbitrary constants that are present, not the powers of the constants, because if you differentiate a or a square, you are finally going to get only the value 0. So, it does not matter as to in what power the constants appear. So, a square and b square are again taken to be two arbitrary constants, and notice that the power of z is also equal to 2. So, how do you go about obtaining the PDE for this expression? Because it contains two constants, again your partial derivatives should be restricted to only p and q. So, we will start the differentiation procedure. On differentiating partially with respect to x, notice that z is the dependent variable, correct. So, when you differentiate z square, what can you expect? When I differentiate partially with respect to x, z square becomes 2z, that is 2z is for the power of z, which is z square, and then z with respect to x will give you dou z by dou x. Okay. It is similar to the normal differentiation of y with respect to x, right. For example, if you have y square equal to 4ax, how do you differentiate y square equal to 4ax with respect to x? You write 2y into dy by dx. Recall friends, why you write dy by dx there? Because y depends on the function or the dependent variable x, because y is dependent on x. So, every time you differentiate y, it will be followed by dy by dx. The same thing is true even here, because the variables, the z is a dependent variable depending on the variables x and y. As and when you differentiate z, it should be followed by the corresponding partial derivatives. That is to say, if you differentiate with respect to x, you write dou z by dou x, and if you differentiate with respect to y, you write dou z by dou y. The same thing is valid when you differentiate with respect to y also. That is, if you differentiate z square with respect to y, what do you do? Z square is 2z, this is for the power, followed by the corresponding partial derivative with respect to y, which is dou z by dou y. Okay, remember this procedure, because z is the dependent variable depending on x and y. So, as explained there, so if I take the given expression and differentiate partially with respect to x, z square will give 2z dou z by dou x is equal to, right side x square is 2x by a square, y is a constant, so that will be 0. So, you are left with 2z dou z by dou x equal to 2x by a square. Here, if you use the notation dou z by dou x equal to small p, I get 2zp equal to 2x by a square. You cancel the 2 on both sides to get this expression, zp equal to x divided by a square. Now, because it contains two constants, let me repeat again, you should restrict your differentiation to only p and q. So, now take the given expression and differentiate it partially with respect to y. So, what happens? The left hand side z square becomes 2z dou z by dou y is equal to 2y by p square, or if you cancel 2, because you can cancel the 2 here, because dou z by dou y has the notation q, you get zq equal to y by b square. The next thing is, after you finish the partial differentiation, how to eliminate the constants a and b. For that, you can just use the given relation here. You have x square by a square plus y square by b square equal to z square. So, what you do? Take the expression in equation 1 and multiply by x on both sides. So, what do you get? When you multiply by x on both sides, this relation transforms to xzp equal to x square by a square. Take the relation in equation 2 and multiply by y on both sides. So, what will that give? yzq is equal to, multiply by y on both sides. So, y by b square becomes y square by b square. Immediately, friends, you can observe that I just have to add the 2, because RHS is after addition equivalent to the given expression. So, that is what you see here, multiplying equation 1 by x and equation 2 by y and adding, we get xzp plus yzq equal to, right side, x square by a square plus y square by b square. But x square by a square plus y square by b square is z square from the given expression. So, that you get the PD as xzp plus yzq equal to z square. Observe that you have z common. So, divide each term by z on both sides. So, finally, you get xp plus yq equal to z is the required partial differential equation. We will go to the next example. From the PDE given z is x square plus a into y square plus b. What we are seeing in these examples is different methods of elimination of the arbitrary constants. How exactly you can eliminate the constants after you do the partial differentiation of the given expression. Now, this expression again contains two arbitrary constants a and b. So, again my partial differential equation will be restricted to only p and q. Let me remind you again, when you find p and q, invariably the PDE will contain both, not only one of them, right. So, when I take the expression and differentiate partially with respect to the variables x and y, first with respect to x, when I differentiate with respect to x, x square plus a gives you 2x, this is a constant. So, you get dou z by dou x equal to p equal to 2x into y square plus b. Then differentiating partially with respect to y, which is equal to q, I get dou z by dou y equal to q, which is now x square plus a is a constant. So, it will remain in the same form, and y square plus b with respect to y will give you 2y. So, the corresponding derivative is 2y into x square plus a. Next, how to do the elimination? Observe that you have x square plus a and y square plus b present in both 1 and 2, and the same or a similar multiplication term exists in the given relation. So, it is obvious that you just have to multiply equations 1 and 2. So, multiplying 1 and 2, left hand side gives me pq, right hand side 2x into 2y will be 4xy into x square plus a into y square plus b, but x square plus a into y square plus b is the given expression z. So, that finally, we get pq equal to 4xyz as the required PD. Let us go to the next example. Now, you will see that the methods of eliminating the arbitrary constants given keep on changing from example to example. Okay. So, here there are two arbitrary constants a and b. I told you earlier that it does not matter in what form the constant appears. Okay. In this case, the arbitrary constant a appears as a square, and the constant b is itself in the form b itself. So, because again it contains two arbitrary constants, we will restrict our differentiation to only p and q. So, differentiating the given relation partially with respect to x and y, we get first, let us differentiate with respect to x. So, z becomes dou z by dou x, which is p, x y differentiation is y, then I have x here. So, y will be out, root of 1 by x, root of x square minus a square is 1 by 2 root x square minus a square into x square minus a square is 2x. You can cancel the 2 here. If you cancel the 2 there and rearrange, you get p equal to y plus y into x, xy divided by root x square minus a square. So, let us call that equation 1. Now, differentiate the given expression with respect to y. So, z becomes dou z by dou y, xy with respect to y is x, then in y root x square minus a square, this is a constant. So, differentiation of y is 1, you get root x square minus a square. If you notice friends, in this process of differentiation, you can observe that once you start the differentiation process, that is you obtained p and q, you can see that the constant b has vanished, correct. So, if the constant b vanishes during the differentiation itself, so for the final PDE, you do not require the given expression. So, this expression will not be used, because the two partial derivatives obtained do not contain b in them. So, you should now try to eliminate the constant from the partial derivatives itself. So, because the two partial derivatives do not contain b, I will try to eliminate a from these two only. I do not require the given expression. So, how to do that? Go to 1, find the value of p minus y. What is p minus y? Shift the y term to LHS, you get p minus y equal to xy by root x square minus a square. Let us call that equation 3. From equation 2, shift the x to LHS, I get q minus x equal to root x square minus a square. You can observe that in 3, root x square minus x square is present in the denominator. In 4, it is present in the numerator. Just have to multiply the two expressions to get the required PD. So, multiplying the two, we get p minus y into q minus x equal to xy, or rearranging or after multiplication you get p minus pq minus px minus yq plus xy equal to 0, cancel xy, which gives you xp plus yq equal to pq, which is the required PD. We will go to the next example. Z is x minus a whole square plus y minus b the whole square, which has two arbitrary constants. So, again our PD will be restricted to only p and q. So, differentiate partially with respect to x. So, LHS z is dou z by dou x, which is also p. In these two terms, y is a constant. When you differentiate, this is 0 with respect to x. X minus a whole square becomes 2 into x minus a. Then differentiate partially with respect to y. Dou z by dou y also equal to q. Now, x is a constant. So, this is 0. Y minus b whole square will reduce to 2 into y minus b. Now, how to eliminate? So, from equation 1 calculate x minus a. X minus a comes to p divided by 2, and from equation 2 y minus b comes to q divided by 2. Substitute these two in the given relation. So, you get z is equal to p square by 4, p by 2 whole square plus q square by 4. Cross multiplying 4 to the LHS, you get 4z equal to p square plus q square, which is the required PD. Now, so far the expressions that were studied contained two arbitrary constants. So, the final PD was of order equal to 1. Let us see a few examples where you have more than two constants. So, the next example, form the PD given z equal to ax plus by plus cxy. So, there are some observations to be made before you actually go to the formation of the PD. First, this relation contains three arbitrary constants a, b and c, which have to be eliminated. So, hence as we discussed earlier, the order of the PD must be clearly greater than 1, it cannot be 1, and you can use this. Generally, order of the PDE will be number of arbitrary constants eliminated, in this case 3 minus 1, so which comes to 2. Hence, in this example we obtain a PDE of order 2, but note that a order 2 PDE can contain one or more of the partial derivatives R, S and T, because a second order PDE is a PDE containing any of these derivatives, any or all or some of them. So, some equations may contain only R, some may contain more than one, okay, that depends on the given expression. Okay, let us go about differentiating this. So, differentiating the given expression partially with respect to x and y. So, I have z. So, z gives me dou z by dou x equal to small p. There are two terms containing x, which are these two. I get a plus cy. That is the partial derivative with respect to x. When you differentiate partially with respect to y, dou z by dou y will be, this is 0 because there is no y term. Then by becomes b and cxy changes to c into x. As I told you friends, you can see the first order partial derivatives, dou z by dou x and dou z by dou y. Now, because you know that the PDE of order 2, you are left with three more partial derivatives, which are dou square dou z by dou x square, dou square z by dou x dou y and dou square z by dou y square. So, let us calculate those things. Dou square z by dou x square is obtained by differentiating dou z by dou x again with respect to x. So, go to this, differentiating expression 1 partially with respect to x, I get dou square z by dou x square, which by notation is r, equal to, there is no x in this, so it is 0. Next, to get dou square z by dou y square, you differentiate dou z by dou y again with respect to y partially. So, I get dou square z by dou y square, it does not contain y in this. So, again that value is 0, which is equal to t. Finally, one more partial derivative remains, which is dou square z by dou x dou y. So, to get that, either differentiate this with respect to y, either differentiate dou z by dou x with respect to y, or equivalently differentiate dou z by dou y with respect to x. Both are identical, both are the same. I get dou square z by dou x dou y. I will do the first one, differentiate this with respect to y. So, what do you get? Dou z by dou x transforms to dou square z by dou x dou y equal to that note, by notation it is s, and the derivative of a plus cy with respect to y is immediately equal to c. Now, we will go about the elimination procedure, right. So, how to do the elimination? So, when the PDE is of order 2 or more, not all the partial derivatives will be necessary during the elimination of arbitrary constants. So, in the problem which we are doing now, the partial derivatives r and t obtained are not necessary, because both are giving you 0 values. You got r equal to 0 and s equal to 0, sorry, t equal to 0, correct. A trial and error method will ensure the correct PDE. You can see when you practice also, not all second order partial derivatives may be necessary when you obtain a PDE of order 2. Okay. You have to do a trial and error method and try to see what partial derivatives exactly fit into the required PDE, right. So, in this case, to obtain the PDE, multiply equation 1 by x, that is you multiply equation 1 by x, which is this equation. You take dou z by dou x equal to p equal to a plus cy, which gives you, when you multiply by x, you get px equal to ax plus cxy. Multiply equation 2 by y, which gives you qy equal to by plus cxy, and then add the 2, right. And finally, observe equation 5, where you have dou square z by dou xy equal to s equal to c. So, that expression will be required to obtain the final PDE. So, when you multiply and add, I get px plus qy as ax plus cxy plus by plus cxy, or slightly rearrange px plus qy, take these 3 terms together as you see here, write px plus qy as ax plus by plus cxy, then the remaining cxy let it be separate. Now, these 3 are the given expression z. So, ax plus by plus cxy is given to be z. So, you can replace that by z, and for the c here you can replace c by the partial derivative calculated already, c as s. So, finally, that gives you px plus qy equal to, this is z, plus c is s into xy, which is the required PDE. We will see one more example where we will eliminate 3 constants. So, form the PDE given x square by s square plus y square by b square plus z square by c square equal to 1. Observe that in this example there are 3 arbitrary constants a, b, c, and hence the order in general is number of constants minus 1, which is 3 minus 1 equal to 2. But this example in particular has 2 simple methods. This example will be solved by 2 methods. Either, as I told you, all partial derivatives are not necessary, either differentiating the given expression twice partially with respect to x, or differentiating the given expression 2 times partially with respect to y, and both methods are equivalent. So, we will illustrate the first method. First method in the sense, by differentiating the given expression twice with respect to x. So, differentiating the given expression partially with respect to x. Observe, it is x square by a square plus y square by b square plus z square by c square equal to 1. So, when I differentiate partially with respect to x, I will differentiate only these two terms. Y is a constant which will be 0. So, x square is 2x by a square, then z square is 2z dou z by dou x by c square equal to derivative of 1 will be anyway constant equal to 0, that you can see here. So, x square is 2x by a square plus z square is 2z dou z by dou x by c square equal to 0, or cancelling 2 because RHS is 0, you get x by a square plus z into dou z by dou x by c square equal to 0. Let us call that equation 1. We will repeat the differentiation again, differentiating 1 again partially with respect to x. First term x by a square reduces to 1 by a square. In the second term, you apply product rule for z into dou z by dou x. So, what do you get? When you apply product rule for z into dou z by dou x, I get z into dou z by dou x will give first z into partial derivative of dou z with respect to x will be dou square z by dou x square, first function into derivative of the second plus second function dou z by dou x which is this into derivative of z with respect to is again dou z by dou x. That is what you see written here, z into dou square z by dou x square plus dou z by dou x into dou z by dou x by c square equal to 0. We will call that equation 2. Now, to form the PDE, we will introduce notations. Because dou z by dou x is p, equation 1 can be written as x by a square plus zp by c square equal to 0. To make the elimination of the constants easier, we will take x by a square on the left, shift it to RHS, you get minus zp by c square, or shift the c square here, you get c square by a square equal to minus zp divided by x. Similarly, use notations in the second equation, I get 1 by a square, this is r, so zr plus this is p into p which is p square by c square equal to 0. Shift the term here to RHS, I get 1 by a square equal to minus of zr plus p square by c square, or this will simplify to c square by a square equal to minus zr plus p square. Observe that equations 3 and 4 have identical left hand side expressions, c square by a square. So, you can equate the RHS also. So, immediately from 3 and 4 the given PDE is zr plus p square equal to minus zp by x by cancelling the negative sign, or zp equal to xzr plus p square becomes the required PDE. It is a PDE of order 2 due to the presence of the partial derivative r. Again, if you follow the second method where you differentiate the given expression 2 times with respect to y, it gives you zq equal to yzt plus q square, where t is dou square z by dou y square. Let us go to some geometrical considerations. The next example, form the PDE of all spheres having radius k and having their centers in the xy plane, or equivalently the plane z equal to 0. So, we have to initially write the equation of the sphere before trying to answer this question. So, first let us recall the equation of a sphere having center at ABC and radius equal to k is x minus a the whole square plus y minus b the whole square plus z minus c the whole square equal to k square. Now, it is given that the center of the sphere is lying on the xy plane, that means the z coordinate of the center is 0, or equivalently c is 0. So, what happens? Since the center is on the xy plane, we have c equal to 0, and hence the equation of the sphere in this example becomes x minus a whole square plus y minus b whole square plus z square equal to k square. There are two things to remember here. One, this expression has the dependent variable z in its powers, that is z square. So, as we illustrated in one of the previous examples, z square will be 2z dou z by dou x or 2z dou z by dou y. Second, the arbitrary const, we have to eliminate the arbitrary constants a and b from this relation, because for different values for of a and b, the center of the sphere changes. If you observe equation 1, according to a and b, the center of the sphere changes, but the constant k need not be removed because it is the radius of the sphere, which is a fixed constant. So, you should understand the difference between what is a arbitrary constant and what is not. So, in this case a and b only are to be removed, not the constant k. So, what you do to remove? Take equation 1 and differentiate partially with respect to x and y, because two constants only p and q will be sufficient to obtain the PDE. So, when you differentiate partially with respect to x, you get 2 into x minus a for x minus a whole square plus z square is 2z dou z by dou x equal to 0. Remove 2, you get x minus a plus zp equal to 0, or x minus a becomes minus zp. Similarly, if you differentiate with respect to y, you get y minus b equal to zq. Because these two expressions contain x minus a and y minus b, we just substitute these two in the given in the relation obtained in equation 1, which is x minus a whole square plus y minus b whole square plus z square equal to k square. So, substituting the values of x minus a and y minus b obtained above in 1, we obtain x minus a whole square is z square p square, because x minus a is z minus zp, y minus b whole square is z square q square plus z square equal to k square, or taking z square common, the result is immediate. Z square into p square plus q square plus 1 equal to k square is the required PDE. Then find the PDE representing all planes that are at a perpendicular distance capital P from a fixed origin. Now, for this we have to recall the equation of the plane with direction cosines lmn. So, the equation of the plane is Lx plus My plus Nz equal to capital P, where lmn are the direction cosines of the normal or the perpendicular drawn to the plane. You have a plane surface, this is the plane surface, this is normal. This normal has direction cosines lmn, and this is the origin. From the origin to the plane, the distance is capital P. That distance is also called the perpendicular distance from the origin to the plane, and this is the normal drawn to the plane. Now, what is the condition for L square, m square and n square? It is known that the sum of the squares of the direction cosines of a line are the sum of the squares of the direction cosines of a line are equal to 1. So, what happens? You should have L square plus m square plus n square equal to 1. So, that expression L square plus m square plus n square equal to 1 will be helpful to form the required PDE. Now, there are two things to remember. First, this problem is related to geometry. Okay? So, you should know the equation of the plane which passes through the equation of the plane with direction cosines lmn. Second, the perpendicular distance from the origin to the plane is required for the formation. So, as I told you friends, the sum of the squares of the direction cosines is 1. So, L square plus m square plus n square equal to 1. So, you should not mistake this problem to contain 3 constants, because n can be written in terms of L and m. So, hence L m n are the arbitrary constants to be eliminated, since n can be expressed in terms of L and m from equation 2 as n square equal to 1 minus L square plus m square. So, you can treat this problem to contain only 2 arbitrary constants. So, again the differential equation can be obtained from P and Q only. So, how to do that? Go to equation 1, which is Lx plus My plus Nz equal to capital P. Differentiate partially with respect to x, you get L plus Np equal to 0. differentiate partially with respect to y, which gives you m plus nq equal to 0. Substitute these two, find L from this. What is L? L is minus np. From equation 4, m is minus nq. Substitute these values in equation 2. Since L square plus m square plus n square is 1, you have n square p square plus n square q square plus n square equal to 1, which gives you the value of n as 1 by root p square plus q square plus 1. Substitute that back here in these equations. Substitute the value of n obtained. So, L is minus np will give you minus p by root p square plus q square plus 1. M is minus nq from this expression. Substitute n, you get minus q by square root of p square plus q square plus 1. Just substitute these values in the given relation to get the required PDE. Now, the question is this. This problem is a geometrical example because it involves the plane in its normal form. This plane is also called the equation of the plane in its normal form. Okay. So, once you have the values of m and n, you have L, you have m. Substitute in the equation of the plane Lx plus my plus nz equal to capital P. So, this is L, this is m, L into x, m into y, you have the y here, plus n is known 1 by root p square plus q square into z equal to capital P, or px plus qy minus z becomes capital P root p square plus q square plus 1, or px plus qy minus z whole square equal to capital P square into p square plus q square plus 1. With this, I conclude my lecture today. Thank you, friends. In the future sessions, we will be looking into more examples of the formation of a PDE. Thank you.